I touched something. Sorry about that. Yeah, let's explain that. So concluding, we actually showed that our thermal processing with dopants resulted in what? It resulted in a stable high-performance catalyst. One thing that I forgot to talk about, and I'm going to kick myself in the pants for that, was that if you looked at the X-ray diffraction patterns, there was no shift in the ruthenium oxide, which essentially meant that we're most likely having a surface reaction. The electrochemistry is all about reactions at the surfaces. So that's not too surprising. And second, this doping gave you the lowest Tafel parameters. So we found that out from the material itself. From our techniques that we use, this EIS technique, we determined that, yeah, you could figure out that the changes of your polarization or your degradation of your catalyst show up beautifully with EIS. Second, we knew that catalysts with the lower polarization resistance and the highest double layer capacitance performed the best, and that actually showed up pretty good. And finally, just some quick notes on our iridium ruthenium oxide system, because we're quite proud of this. And that's basically that 9% is about where you want it to be, 9–10%, and gave you an improvement of around 35 millivolts over a wide spectrum of operating current densities. So that's the conclusion of my presentation, and I'm willing to take some questions. But first, I want to acknowledge that this was actually done by quite a big group. Myself, Keith Billings, who's also a USC student, Samad Ferdowsi works at JPL, Jess Sakamoto, who's at Michigan State University, Professor Mansfeld oversaw this work, and he's from the Corrosion Environmental Effects Laboratory, and my boss at JPL, who's named Dr. S.R. Narayan. And with that, I'll take some questions.
We have time for questions or comments.
Who's the supplier of the commercial iridium ruthenium?
I wouldn't say, sir. I can't say that. You're talking about it's because it's a vendor, and it just wouldn't be fair to them. But there are three big groups in the United States. One's called Proton Energy Systems. The other is called Lintech, which is in College Station, and there's Giener, which is in Boston, Massachusetts. And out of the three, only one of them does iridium ruthenium oxide, and they are actually the best.
How available is ruthenium?
Ruthenium is more expensive than platinum at times. So I don't know about its availability, which is why...
Is that at the metal stage or at the...
at the ore stage?
At the ore stage, the outside.
Yeah, I haven't looked at that so much, but I did know that it is expensive. I'm not gonna skate around that, and that's why we developed something like, for instance, this lead-based system, which is dirt cheap. I shouldn't say dirt cheap because it's not.
It's relative.
Yeah, it's a lot cheaper, that's for sure.
Has anybody tried platinum?
Oh, absolutely.
Like, for instance, on your periodic chart, ruthenium goes right after iridium, and then there's rhodium and platinum and palladium.
Well, believe it or not, platinum iridium oxide is what the space industry considers the standard. But it's not the highest performance. It is just the absolute most stable.
Any other questions?
Yes, sir.
So basically, iridium and lead take out the oxide of oxygen from the nucleus.
That's what we're hoping.
Right. And why after those oxygens are taken out from ruthenium oxide, why the unstoichiometric
Why should it stay?
Is stable?
God, that's a real beautiful question. Can I answer that? Okay. Okay, so if we just look at this, I'm just going to get to the equation. Let me just get to the first one that we could see. Okay, there's the equation right there. So the question was, this material that we're trying to make, this MORUOX, why is that stable? Because whenever you evolve oxygen on a material surface, it's going to become an oxide anyways. So the gentleman's question was, okay, so you have the stoichiometry, why is that happening? Well, what happens is the metal, you're hoping, pins this ruthenium oxide to a lower valence state. When I talk about ruthenium oxide, it's in valence state 4, and I'm trying to shove it to valence state 3. So non-stoichiometric is kind of like, how can you say, you're saying it a little bit tongue-in-cheek. You really just, what you really want to say is you want to just get this to the proper valence state, and you want a material that can hold it there. Because if you don't, that ruthenium oxide could go to other valence states. It could be in 6, it could be in 8. 8 is actually a gas. And that's why it's so unstable to begin with. You just want to make sure you can pin it down. And lead and iridium happen to be two materials. Tin is another that I studied that actually keep it pinned.
But MORUO is that a single phase?
It's a solid solution. That's what we try. Yeah. As a matter of fact, we were hoping it was. And as I showed you, actually, this is the XRD data that actually shows it. You can see here's your ruthenium oxide material. There's no shift in lattice parameters. So we're actually seeing that this must actually be a skin effect. And we're trying to do some XPS to nail that down, just to make sure that this is We didn't have a good technique to measure just the surface of the material itself. I hope that.
That's a big thing.
Yes,
What is the typical value for the X?
Typical value for the X, I took it off of here, it's around 5%. That's what we were shooting for. But we saw that 10% was even better. Point one?
I mean the
Point
division.
one.
So 2 minus 0.1.
Something like this, yeah. You just want a little bit. You don't want too much. Because you don't want to, as we showed in the graph, when we're heating the material up and up and up, making more ruthenium oxide, it becomes less active. So you really want this non-stoichiometric, that's what the active component.
All right, well, let's thank Thomas again. Very good.